Okay, so here's your multiple choice questions. Here's the first one. It says that an odd number will come up twice as often as an even number in the long run. So when I'm writing this out, I need to think that it's going to redefine my sample space, where odd numbers, like the number 1, are twice as likely to occur as even numbers, like the number 2. Odd numbers 3, twice as likely to occur as even numbers 4. And the same works with 5 and 6. If I count all my possibilities, now that gives me 9 outcomes. So I only have 2 possibilities, C or D, for my answer. The odds are twice as likely to occur. So a 1 would occur 2/9 of the time, where a 2 would occur 1/9 of the time. Same with the 3, 4, 5, and 6. So my answer to number 1 is D. If you struggle with number 1 at all, you want to really focus on identifying what your sample space is. I mean, that's the major component of these types of problems. Let's move on to number 2. Number 2 and 3 go with this survey of students enrolled in a small college. And they ask how much time they spend on the internet during a typical day. And we're going to say that this data is a representation of our college. We can see that the answers are listed for 2 and 3, but let's make sure that we understand how we got to these. It says, what's the approximate probability that a randomly selected student at this college is female that spends no time on the internet in a typical day? So we're not saying that it's a female given that they spend no time. It's a female and they spend time. So I'm looking for their intersection of female and no time. So here's my female row, and my no time on the internet column is right here. So where they intersect, or where they overlap, is right here. It's 10 out of my total, which is 100. It's because it's an intersection. It's not asking for a given probability. Okay. If I look at part 3, it says, or number 3, it says if a randomly selected student is male. So we're basically saying that we know that this student is male. So our sample space has effectively been reduced to 65 people. So I know this one's going to be out of 65. Okay. If a randomly selected student is male, what's the approximate probability that he spends 1 or more hour on the internet in a typical day? So the probability 1 or more, so I'm going to put greater than or equal to 1, given that we have a male, is equal to something over 65. Well, it's their intersection, the intersection of a male and 1 or more. So that's where we're going to use 30 out of 65. Okay, and that's where the answer C comes from in your textbook. So the answer to number 2 is E. More importantly, how did we get that? And the answer to number 3 is C. Again, more importantly, how did we get that? For number 4, it says, under what conditions must it be, or is it true that the probability of A or B is equal to the probability of A plus the probability of B? Well, we know this formula holds true for every single possibility. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So we can put an intersection, or we can write and. They're the same thing. So I'm going to write and here. But we know that this is the same as probability of A union B, and this is the probability of A intersection B. Well, the only time that we're not going to have to write this A and B is when they don't intersect. And the only time they don't intersect is when they are mutually exclusive. And that's why number 4 is A. Number 5, under what conditions is it true that the probability of A and B is equal to the probability of B given A times the probability of A? We also have this formula, and this is the other formula from this chapter that is important. So the probability of B given that A has occurred is equal to their intersection, okay, over the probability of this second term, because it's given that that has occurred, that becomes my sample space. Okay. If I just do some simple multiplication, I get this. Probability of A times the probability of B given A is equal to their intersection, probability of A intersection B. And that works anytime. That formula works no matter what. There's no conditions necessary. That's a true statement any and every time. Okay? The only time there are conditions necessary is if we are independent. If we are independent, then this is true. The probability of A times the probability of B is equal to their intersection. But if we are independent, it means that A occurring does not do anything. It doesn't change B. It doesn't have any bearing on what B's probability is. So these two, if they're independent, are the same. And that's why we're allowed to write this if they're independent. So there would be a condition here on independence, but there's no condition here because this happens every time. Moving on to number 6, we have 30 males and 20 females in a stats class. 10 of the males and 10 of the females are also currently enrolled in a science course. If students selected at random from those enrolled in the statistics class, what's the probability that a female is selected? Okay, so we're first just starting with our stats class. We have in our stats class, we have a total of 50 people, 20 of which are female, 20 out of 50, that's 0.4. Okay? Now they give us the same conditions and they say if a student is selected at random from those enrolled in this statistics class, what's the probability that the selected student is a male who is also enrolled in a science course? So what we're looking for now is the probability of a male and science. Okay? Now there's no given probability, there's no conditions here. It's just saying that the probability of male and science. Well, if I look at this again, my sample space is still 50. It's all people. The people that are males and enrolled in the science class are only the 10. 10 males that are enrolled in the science course. 10 out of 50 is 0.2, and that's where this answer comes from. Okay? Let's move on to number 8. Same conditions again. It says a student selected at random from those enrolled in the 6th class, given that the student is female. So we know now that we have a female student. Okay? Given that the selected student is female, what is the probability that the selected student is enrolled in a science course? Science course. Okay? Our sample space now is our 20 females. Out of our 20 females, 10 of them are also currently enrolled in a science course. 10 are enrolled in a science course. 10 out of 20 is 0.5. That's where this answer comes from. Again, these are all just basic counting problems. When it says given, it reduces our sample space to what those values are. Let's move on to number 9. Okay, so this is the one about the credit card. Basically says 60% of the students carry more than one credit card. There's two possible outcomes here. You have more than one credit card and does not have more than one credit card. It says which of the following would be a correct assignment of random digits to the outcomes in order to simulate selecting a student at random from students enrolled at the university. Well, if there's 60, so the probability of carrying more than one credit card, I guess it's more than one. It doesn't say more than one is greater than, is 0.6. So the probability of having less than or equal to 1 is 0.4. So I need to assign random digits that are going to assign them in a way that represents this population. So I need 60% of my random digits to be more than 1 and 40% to be less than or equal to 1. So it says 0 represents more than one credit card, 1 represents not more than one credit card, ignore all other digits. The problem is this is assigning equal 50-50 probability, that one's out. Odd digits represent more than one credit card and even digits represent not more than one credit card, again 50-50, that's out. 0, 1, 2, and 3 represent more than one credit card, 4, 5, 6, 7, 8, and 9 represent not more than one credit card. They've got our probabilities flipped This is giving greater than 1.4 and less than or equal to 1.6, so that one's out. 0, 1, 2, 3, 4, 5, that is 6 numbers represent more than one credit card, and 4 numbers represent not more than one. That is the one that works correctly. It's assigning 60% of the numbers to more than one and 40%. So it'll correctly simulate what our population is. Number 10, which of the following is a correct assignment of random digits to the outcome of heads and tails in order to simulate a fair flip of a coin? 0 represents heads, 1 represents tails, ignore all other digits. Each one is equally likely to occur, so this one works. Odd digits represent heads, even digits, that's fine as well, equally likely to occur. 0, 1, 2, 3, 4, there are 5 of them, 5, 6, 7, 8, and 9, there are 5 of them, 5 and 5, equally likely to occur. Only B and C above are correct. Even though A is kind of a waste of time going through all those digits that wouldn't be there, it's still a correct assignment. So D's out, our answer is E. Okay. Which of the following statements is true for 2 events, each with a probability greater than 0? If the events are mutually exclusive, they must be independent. This is a statement that's completely false. If the events are mutually exclusive, they cannot be independent. Mutually exclusive events do not intersect. There are 2 events, A and B, that cannot happen at the same time. Okay? Independent events always overlap. Mutually exclusive is dependent. It's part of the family of dependent events, whereas independent events cannot possibly be mutually exclusive. So that also makes us cross out B. If the events are not mutually exclusive, they must be independent. That one's false as well. If they're not mutually exclusive, they could be independent, but they could also be dependent. Dependent events can overlap. They just don't overlap to the point where this intersection is the probability of A times the probability of B. So this one is out. If the events are not independent, they must be mutually exclusive. Again, we just said dependent events can overlap, so that's out. So our answer there is E. All right, let's move on to number 12. And this is the first one that dives into Bayes' rule a little bit. It says the Air Force receives 20% of its parachutes from Company 1, 55 from Company 2, and the rest from Company 3. Now, when you see those percentages and they're all mutually exclusive, you should maybe start to be thinking Bayes' rule. I can't get a parachute from Company 1 and Company 2 at the same time. So they're all 3 mutually exclusive. It's usually either 2 or 3 events. So probability of Company 1 is 0.2. Probability of Company 2 is 0.55. And the probability of Company 3 is what's left over. And what's left over seems to be 0.25. It says the probability that a randomly selected parachute will fail to open is 0.0025, 0.002, and 0.0022, depending on whether it's from Company C1, C2, or C3, respectively. If a randomly chosen parachute fails to open, what's the probability that it is from Company 3? So here's what we're asking. What's the probability it's from Company 3, given that it fails to open? Okay? So that means my sample space is going to be everything that fails to open. So let me start working on this. So if it came from Company 1, it can fail to open, or it cannot fail to open. I guess we would really hope that it wouldn't fail to open, but there is that possibility. The probability of failing to open is 0.0025. So that would be 0.9975, the likelihood it doesn't fail to open. The probability that it fails to open, given that it's come from Company 2, is 0.002. Again, the not failing has to go in here, and that would be 0.998. And then the probability that it fails to open, given it's from Company 3, is 0.0022. And the probability that it does not fail to open, given that it's from company 3, is 0.9978. So I've written out all possible events. Okay? What I'm really just concerned with are the ones that failed to open. So here from company 1, this failed to open. Here it failed to open, and here it failed to open. So those are all 3 of my possibilities. Those are my sample space. Those are my denominator. So my denominator now is, it could come from company 1 and fail to open. So I have to multiply those two. 0.2 times 0.0025 plus, it could come from company 2 and fail to open. So it's like company 1 and fail to open, or company 2 and fail to open. Remember, and means multiply, or means add. So this is 0.55 times 0.002. I think I'm going to be running out of space here in a second. And the last one could come from company 3, 0.25, and fail to open, 0.0022. Okay? Now the only place that I have success is if it comes from company 3. So that's here. Here's coming from company 3 and failing to open. So my numerator is 0.25 times 0.0022. Okay? And you can plug this in your calculator. You plug it in your calculator, you should get E, 0.256. I recommend you do the numerator first, write down that value, then do the denominator, write down that value, and then do your division, and that should work. Just don't round off too much, because if you round off too much, you might get round off error, and you might get D when you should have gotten E. Okay, events A and B, with the probability of A is 0.6, probability of B is 0.7, the probability of A intersection B is 0.4. Which of the following is true? Events A and B are mutually exclusive. They can't be mutually exclusive. They intersect. They're independent. If they're independent, then the probability of A times the probability of B should equal their intersection. Well, if I'm looking at this, A is 0.6, B is 0.7, their intersection is 0.4, and when I multiply these together, I get 0.42. And that does not equal 0.4. So that means they are not independent. Their union is 0.6 plus 0.7. Again, our formula tells us that it's not that. Their union is 0.6 plus 0.7 minus their intersection. So they're missing that part there. So that one's out. Probability of A given B is equal to the probability of A. This would be true if they were independent. So that makes this a false statement as well. So E is my only correct statement. Number 14. 2 coins, a nickel and a dime, are to be flipped. Consider the following event. A is the nickel lands with the head side up. B is the dime lands with the head side up. Which of the following is true? The events A and B are independent and mutually exclusive. Again, independent and mutually exclusive cannot happen at the same time. So this is a false statement. The events A and B are neither independent nor mutually exclusive. So I guess I've got to think about this. Are a nickel and a dime are flipping them independent. So is the probability of A times the probability of B equal to their intersection, A intersection B. So the probability of event A, a nickel landing head side up, is 1/2. The probability of event B, a dime landing head side up, is 1/2. The entire sample space is, if I flip my nickel first, with the nickel I could have heads or tails, and then with my dime, so those are my 2 events, I could have a heads or a tails, a heads or a tails. The probability of them both landing head side up is right here. That's 1 outcome out of 4. That's the probability of A and B happening. Okay? So 1/2 times 1/2 is 1/4. So those 2 events are in fact independent. If they are independent, then this is a false statement. The events A and B are independent. That's a true statement, but not mutually exclusive. That's a true statement. So our answer has to be C. I could go through the rest of the answers, but that just seems like a little bit of a waste of time. 15. Chance experiment involves selecting a person at random from those who purchased a new car at a particular dealership, and noting both the gender and whether or not the person purchased a hybrid vehicle. The sample space for this experiment is male who purchased a hybrid, male who did not purchase a hybrid, female who purchased a hybrid, and female who did not purchase a hybrid. Under what conditions would the 4 outcomes in the sample space be equally likely? Okay, let's think about this. I could have a male, and they could purchase a hybrid. I guess I should write this as male or hybrid given male, and then hybrid given male, or hybrid complement given male. I'll get this right. And then I could have a female, hybrid given female, and hybrid complement giving female. So that's all 4 events, right? So male who purchased a hybrid, male who did not purchase a hybrid, female who purchased a hybrid, and female. So this is all 4 of my events, right? Under what conditions would the 4 outcomes in the sample space be equally likely? There are definitely conditions necessary. They're not all equally likely. There must be an equal number of males and females who purchased the car from this dealership during 2010. My sample space of males and my sample space of females would have to be the same in order for this to work out for me here. So that definitely is necessary. 50% of the males must have purchased a hybrid. I think they're missing the part here with that 50% of females also would have had to purchase a hybrid. So I think my answer here is D. D and B, I'm sorry. There must be an equal number of males and females who purchased the cars from this dealership, and 50% of the males and 50% of females must have purchased a hybrid. So both B and D have to be true, so that's why the answer is in fact E. And you could try this. You could say, okay, well, what if there were 100 males, 50 of which who purchased a hybrid, and 50 that didn't, and there were 200 females, 100 of which purchased a hybrid, and 100 of which that didn't. Okay, now each outcome is not equally likely because in my sample space there are 300, but the likelihood of a female not purchasing a hybrid is 100 out of 300, and the likelihood of a female purchasing a hybrid is 100 out of 300, whereas these male likelihoods would be 50 out of 300 and 50 out of 300. That's not equally likely. Okay, so if I go back and change this, let's say I erase these probabilities, and I erase these values, okay, and I make this the same, 100, 50, 50. Now there are only 200 people here, 50 of which purchased a hybrid, 200, 50 of which 200, 50, and 250. So you can see the difference when they have an equal number of trials and when they don't. Every outcome is equally likely. So that's why it had to have both conditions, the equal number and the 50% male and 50% female. So that takes care of the multiple choice questions. The next video will be on the free response questions.